In your AS level studies, you mastered kinematics and dynamics under conditions of constant acceleration, but the real world is rarely so rigid. Welcome to the physics of periodic motion. Oscillations are the heartbeat of the physical universe, from the macroscopic swinging of a pendulum in a grandfather clock to the microscopic vibrations of atoms in a quartz crystal. Periodic motion is everywhere. When a bridge sways in the wind or a car suspension compresses over a bump, the forces, and therefore the accelerations, are constantly changing. This unit introduces you to the physics of systems where the restoring force changes with position. We will build a perfect mathematical model of periodic motion and then progressively introduce real-world complications like friction and external driving forces.
We begin with the idealized baseline for all periodic motion, simple harmonic motion. Everything in this unit stems from one mathematically beautiful defining equation. Simple harmonic motion occurs when an object's acceleration is directly proportional to its displacement, but in the opposite direction. That minus sign is absolutely crucial. It represents the restoring nature of the force, always pulling the object back towards equilibrium. You will learn to translate this physical movement into trigonometric functions, allowing you to predict exactly where an oscillator will be, how fast it is moving, and its acceleration at any given moment in time. Once we have the motion mapped out, we follow the energy. Because the forces change with position, the velocities change, meaning the energy of the system is constantly shifting. You will analyze how potential energy and kinetic energy seamlessly interchange as the object moves back and forth. Crucially, in an ideal system, the total energy remains absolutely constant, forming a perfectly horizontal line on your graph. In the exam, mastering these perfectly parabolic energy curves is a fantastic shortcut. It allows you to calculate velocities and positions quickly without getting bogged down in complex trigonometry. Next, we bring our perfect mathematical model into the messy real world. Ideal systems do not exist in a vacuum. In reality, friction and air resistance drain energy from oscillating systems, a process known as damping. You will explore how this causes the amplitude to decay over time, while the period remains largely unaffected. We will also look at the precise exam definitions for light, heavy, and critical damping. Critical damping is particularly important. It is the exact engineering principle used to design safe car suspensions that return to equilibrium without bouncing, and automatic door closers that shut smoothly. Finally, we look at what happens when you pump energy back into a system. When an external periodic force drives a system and that driving frequency matches the natural frequency of the object, you get resonance. This is a dramatic and sometimes highly destructive increase in amplitude. You will learn to evaluate amplitude frequency graphs, identifying the exact conditions for resonance. More importantly, for the top grades, you will predict exactly how varying degrees of damping alter these resonance curves, not just flattening the peak, but shifting it slightly to a lower driving frequency. This unit bridges the gap between pure mathematics and observable physics. By the end of it, you will be able to